The universe is not just expanding, it is accelerating, and this single fact shatters our most fundamental understanding of physics. We are about to journey through 30 incredible facts that reveal just how bizarre and mysterious our cosmos truly is. You will discover why scientists are confronting a crisis in cosmology and what this means for the ultimate fate of everything. How could a force we cannot see be tearing the cosmos apart? And what does it mean that our universe is mostly made of stuff we can never touch? What single cosmic question would you most want answered? Edwin Hubble peered through the giant telescope at Mount Wilson and saw something that would change everything. He noticed that distant galaxies were not simply drifting in the void. They were all racing away from us, and the farther away a galaxy was, the faster it seemed to be receding. This was not a random motion. It was a pattern, a cosmic rule we now call the Hubble Law. The key evidence was written in the light from these galaxies. Their light waves were stretched, shifting toward the red end of the spectrum, much like the sound of a siren drops in pitch as a police car speeds away from you. This redshift was the undeniable signature of a universe in motion, but this is where it gets truly strange. The galaxies are not just moving through space like cars on a highway. Space itself is stretching, carrying the galaxies along with it. Think of a loaf of raisin bread baking in an oven. As the dough rises, every single raisin moves away from every other raisin. It is not that any one raisin is special, but the entire fabric of the dough is expanding. In our universe, we are not at the center of this expansion. From any raisin, from any galaxy, you would see all the others moving away, painting a picture of a cosmos that is fundamentally and relentlessly growing. This idea of an expanding universe leads to one of the biggest misunderstandings in all of science. We call it the Big Bang, and that name paints a picture of a cosmic bomb exploding in a dark, empty void, flinging galaxies outward from a single central point. That picture is completely wrong. The Big Bang was not an explosion in space. It was the rapid expansion of space itself. There is no central crater, no point of origin you can point to and say, the universe started right there. Instead, think back to the surface of that rising raisin bread. If you were a raisin, you would see every other raisin moving away from you. From your perspective, you would feel like you were the center of the expansion. And here is the profound truth. Every single raisin, every single galaxy has that exact same view. Every point in the cosmos appears to be the center from its own perspective. This is not a trick of the light. It is a fundamental feature of the universe's geometry. The very fabric of reality is stretching uniformly everywhere at once. So when we look out and see every distant galaxy speeding away from our Milky Way, we are not seeing evidence that we are special. We are seeing proof that we are not. We are just one raisin in a cosmic loaf that is getting bigger everywhere at the same time. This realization forces us to abandon the idea of a center entirely, pushing our minds to grasp a universe that is finite yet has no edge and is expanding without expanding into anything. This expansion has a speed, a precise number that tells us how fast the cosmos is stretching. That number is known as the Hubble Constant, and it is one of the most important figures in all of cosmology. Think of it as the universe's current growth rate, a measure of how much faster a galaxy appears to move away from us for every additional megaparsec of distance. A megaparsec is an almost unimaginable unit of length, about 3.26 million light-years. So if the Hubble constant were 70, it would mean a galaxy 1 megaparsec away recedes at 70 kilometers per second. A galaxy 2 megaparsecs away would be fleeing at 140 kilometers per second, and so on. This single number is the master key that unlocks the scale of the cosmos. By measuring how fast the universe is expanding now, we can run the cosmic film in reverse, calculating backwards to estimate the moment it all began. This is how we arrive at the universe's age, roughly 13.8 billion years. It also tells us the size of the observable universe, a staggering 93 billion light-years across. Yet for such a foundational number, it holds a deep and troubling secret. Scientists have spent decades trying to pin down its exact value using two different sets of cosmic rulers. One method looks at the ancient universe at the faint afterglow of the Big Bang. The other measures distances to stars and galaxies in our more recent cosmic neighborhood. These two methods, both incredibly precise, do not agree. They give two different, stubbornly conflicting answers for the Hubble constant. This is not a small rounding error. It is a glaring discrepancy that cosmologists call the Hubble tension, a fundamental rift in our understanding that suggests we might be missing something profound about the laws of physics themselves. That precise number, the Hubble constant, was supposed to be a fixed rule of cosmic growth, but in 1998, two teams of astronomers made a discovery that shattered this expectation, a finding so bizarre it would eventually earn them the Nobel Prize. They were not looking for this. They were using distant supernova, the titanic explosions of dying stars, as cosmic mile markers. By measuring how bright these supernova appeared from Earth and comparing that to their known intrinsic brightness, the scientists could calculate their distance with incredible precision. They could also measure their redshift, telling them how fast the universe was stretching when that starlight began its journey billions of years ago. Everyone expected to find that the expansion was slowing down. After all, gravity has been pulling the cosmos together since the very beginning. The collective tug of all the galaxies, all the dark matter, should have been putting the brakes on the universe's outward rush. But the data told a radically different story. The most distant supernova, the ones whose light had been traveling for billions of years, were fainter than they should have been. This meant they were farther away than anyone had predicted. The only possible explanation was staggering. The expansion of the universe was not slowing down. It was speeding up. Over time, the cosmos was stretching faster and faster. This was like tossing a ball into the air and watching it not only fail to fall back down, but instead shoot away from you at an ever-increasing velocity. It defied all logic. Gravity, the force that governs the cosmos, is an attractive force. Nothing in our known physics could cause space itself to stretch at an accelerating rate. This discovery pointed to the existence of something entirely new, a mysterious, repulsive force that permeates the vacuum of space itself, a force powerful enough to overcome the collective gravity of the entire universe. Scientists gave this unknown force a name that reflects our profound ignorance. They called it darkenergy. This mysterious force, dark energy, is now the prime suspect for the cosmic acceleration. It is not a substance floating in space. It is a property of space itself, an energy inherent to the vacuum of nothingness. The emptier space becomes as the universe expands, the more of this dark energy seems to exist. Its key property is a kind of negative pressure. Think of positive pressure like in a balloon, pushing outward and making the balloon expand. Dark energy acts like a negative pressure, a sort of cosmic suction that actively stretches the fabric of space-time. The more the universe grows, the more this repulsive gravity takes over, driving the galaxies apart at an ever-increasing rate. The most staggering fact is its sheer dominance. Our entire familiar world, every star, planet, and galaxy, every speck of dust, and even all the invisible dark matter, makes up only about 32% of the cosmos. Dark energy constitutes the other 68%. It is the majority ruler of the universe's energy budget, the main component of everything that is. And yet, we have no idea what it actually is. We see its dramatic effects on the largest scales, we feel its gravitational push, but its true nature remains one of the greatest unsolved mysteries in physics. We are living in a universe mostly made of a force we cannot see, touch, or comprehend, a force that is ultimately determining the fate of everything. Ironically, the key to this accelerating universe was written into the cosmic rulebook nearly a century before its discovery by none other than Albert Einstein. When he applied his new theory of general relativity to the entire cosmos, he faced a problem. His equations insisted that the universe should be either expanding or contracting, pulled by its own gravity. Yet the scientific consensus of his time, including his own belief, held that the universe was eternal and static. To force his equations into alignment with this static model, Einstein introduced a fudge factor, a term he called the cosmological constant, represented by the Greek letter lambda. This constant was a repulsive force, a kind of anti-gravity that worked against the pull of matter on the largest scales, perfectly balancing the universe to keep it still. Later, when Edwin Hubble's observations confirmed the universe was indeed expanding, Einstein realized his intervention had been unnecessary. He famously discarded the cosmological constant, calling it his greatest blunder. He had missed the chance to predict the expanding universe, but the story does not end there. The discovery of cosmic acceleration in the late 1990s turned this entire narrative on its head. Scientists realized that the mysterious dark energy pushing the galaxies apart behaves exactly like Einstein's discarded constant. That mathematical term he invented to keep the universe static is, in fact, the most accurate description we have for the force that makes the universe dynamic, driving its accelerating expansion. His greatest blunder was not a mistake at all. It was a stunning premonition, a piece of physics he discovered decades before the universe itself revealed it was needed. The genius was not in the error, but in the tool he left behind, a tool we are still using today to try and pry open the secrets of dark energy. To measure the vast emptiness between galaxies, astronomers needed a cosmic ruler, a reliable way to gauge distance across millions of light years. They found this tool in the stars themselves, in special classes of objects known as standard candles. The most crucial of these are Cepheid variable stars. These are stars that pulse rhythmically, growing brighter and dimmer over a regular period. In the early 1900s, the astronomer Henrietta Leavitt discovered a beautiful and powerful relationship. She found that the longer the pulsation period of a Cepheid, the higher its true intrinsic brightness. Think of it like a lighthouse with a predictable flash. If you know the exact pattern of its beacon, you can calculate how far away it is by how dim the light appears when it reaches you. A Cepheid star's pulse period tells you its true wattage, and by measuring how faint it looks from Earth, you can work out its distance with remarkable precision. This was the first crucial step on the cosmic distance ladder, allowing Edwin Hubble to measure the distances to nearby galaxies and discover the expansion of the universe. But to peer back to the era of cosmic acceleration, scientists needed a beacon visible across the entire universe. For that, they turned to the most powerful standard candle of all, the Type Ia supernova. These are thermonuclear explosions of white dwarf stars that have been pushed over a critical mass limit. Because the explosion always happens at the same tipping point, these supernovae all have nearly identical peak brightness. They are like cosmic flashbulbs, all firing with the same incredible intensity. When astronomers spot one of these events in a distant galaxy, they know its true, phenomenal brightness. By measuring how dim it appears to our telescopes, they can calculate a precise distance to its host galaxy. Then, by looking at the redshift of that galaxy's light, they learn how much the universe has stretched since the moment the supernova exploded. It was this powerful one-two punch, comparing the distance from standard candles to the velocity from redshift, that revealed the universe's shocking secret. The most distant supernovae were too far away, their light too faint. The only explanation was that space itself had stretched more than expected over its long journey, proving that the expansion rate was not constant but accelerating, driven by the mysterious push of dark energy. These cosmic mile markers, from Cepheids to supernova, are not used in isolation. They form the rungs of a delicate structure astronomers call the cosmic distance ladder. To measure the vast scales of the universe, you cannot use just one tool. You need a sequence of methods, each one carefully calibrated by the one below it, allowing us to climb from our own solar system out to the edge of the observable cosmos. The first rung of this ladder is a technique called parallax, something you can demonstrate with your own finger. Hold a finger up close to your face and close one eye, then switch eyes. You will see your finger appear to jump back and forth against the background. Now try the same thing with your finger held at arm's length. The jump is much smaller. Astronomers use this same principle by observing a nearby star from opposite sides of Earth's orbit around the Sun. The tiny shift in the star's apparent position against more distant stars allows for a direct geometric calculation of its distance. This is our most fundamental ruler, but it only works for the very closest stars. To reach beyond our galactic neighborhood, we need a brighter beacon. This is where the second rung comes in, the Cepheid variable stars. We find Cepheids within those nearby galaxies whose distances we already know from parallax. By carefully measuring a Cepheid's pulsation period and its apparent brightness from Earth, we can firmly establish the period-luminosity relationship for all Cepheids. We lock in their true wattage. Once calibrated, any Cepheid we see in a more distant galaxy becomes a powerful distance indicator. Its pulse tells us its true brightness, and its faintness reveals how far away it is. But even Cepheids eventually fade from view at immense distances. For the final, longest reach across cosmic time, we rely on the third rung, the type Ia supernova. These are the flashbulbs that illuminate the early universe. And how do we know exactly how bright they are? We calibrate them using Cepheids. Scientists find galaxies within range of both methods, galaxies that contain both Cepheid variables and have also hosted a type Ia supernova. By using the Cepheids to measure the precise distance to that galaxy, they can confirm the true, phenomenal brightness of the supernova that exploded there. This painstaking process ties the entire ladder together. Each rung depends entirely on the accuracy of the one below it. A tiny mismeasurement in the parallax of a single star creates a small error in calibrating the Cepheids. That error then magnifies when applied to the supernova. These accumulated uncertainties are a primary source of the Hubble tension. The local measurement of the expansion rate, built carefully rung by rung up this cosmic ladder, gives one answer. The measurement from the early universe using the cosmic microwave background gives another. The gap between them suggests that perhaps a rung on our ladder is slightly warped, or worse, that the ladder itself is resting on a foundation we do not yet fully understand. While one team of astronomers was building the cosmic distance ladder, another was looking back to the very beginning. The Planck satellite, a European Space Agency mission, was designed to stare at the oldest light in existence. It mapped the cosmic microwave background, the faint afterglow of the Big Bang itself. This ancient glow fills the entire sky, a cold relic from a time when the universe was a hot, dense plasma, just 380,000 years old. Planck did not just see a uniform fog of radiation. It measured minuscule variations in temperature, tiny hot and cold spots imprinted on this cosmic canvas. These fluctuations are like fossilized sound waves from the infant cosmos, the seeds from which all future structure would grow. By analyzing the precise pattern of these spots, their sizes and distributions, scientists can deduce the fundamental ingredients of the early universe. They can calculate how much ordinary matter, dark matter, and dark energy were present at that primordial moment. This gives them the initial conditions, the starting recipe for our cosmos. Plugging these pristine conditions into our best models of physics, they can run the cosmic film forward, predicting exactly how the universe should have evolved over 13.8 billion years. This includes a precise prediction for the Hubble constant, the universe's expansion rate today. The result from Planck is incredibly precise, a single number derived from the universe's baby picture. Yet, this number from the dawn of time stubbornly disagrees with the measurement we get from our local neighborhood. The early universe tells one story about how fast the cosmos is expanding, while our modern observations tell another. This is not a minor disagreement. It is a fundamental crack in the foundation of cosmology, a direct challenge to our most successful model of the universe. Either there is a hidden error in our painstaking measurements, or the universe itself contained something in its infancy that our standard models do not account for. What could possibly have changed between then and now? This disagreement is the Hubble tension, and it is far more than a simple measurement error. It represents a full-blown crisis in our understanding of the cosmos. On one side, we have the pristine data from the Planck satellite, a picture of the infant universe that gives us one very precise value for the Hubble constant. On the other side, we have the painstaking work of building the cosmic distance ladder with stars and supernova, which gives us a different yet equally confident value. The gap between them is real and it is not going away. Imagine two of the world's most accurate clocks, both built by master craftsmen, both ticking with perfect precision, yet one consistently runs just a few seconds faster than the other. The problem is not with the clocks themselves. The problem is that our fundamental understanding of time might be flawed. This is the situation cosmology now faces. Our two most trusted methods for telling the universe's expansion rate are giving us conflicting times. One possibility is that there is a subtle, hidden mistake somewhere in our measurements. Perhaps our understanding of Cepheid stars is not quite perfect, or maybe there is an unknown type of dust in galaxies that makes distant supernova appear slightly dimmer than they really are. But after years of checking and rechecking, no one has found a simple error large enough to close the gap. This leads to the far more exciting and unsettling possibility. The Hubble tension might be our first real evidence that the standard model of cosmology, our current rulebook for the universe, is incomplete. The model, which beautifully explains so much of what we see, might be missing a vital ingredient. What could that ingredient be? Perhaps dark energy is not constant as Einstein imagined, but is evolving, growing stronger over time. Maybe there is a new, previously unknown type of subatomic particle that flooded the early cosmos, subtly altering its expansion history. Or it could be that dark matter interacts with itself in ways we never predicted. Each of these ideas is a potential crack in the foundation of modern physics, and the Hubble tension is the chisel that is prying it open. This is not a sign that science is failing. It is the thrilling sound of a frontier being pushed, a mystery so profound that its solution will likely rewrite the textbooks. So what are these exotic ingredients that could fix our cosmic recipe? One leading candidate is something called dark radiation. We know about ordinary radiation, like the light and heat that filled the early universe. Dark radiation would be a new, invisible form, perhaps a new type of ghostly neutrino that streams through the cosmos without interacting with almost anything. In the universe's first moments, this extra radiation would have changed how fast the primordial plasma expanded and rippled. Adding just a little bit of this dark radiation to our models of the early universe can subtly alter the predicted expansion rate, potentially nudging the Planck measurement to align with what we see locally. It is like discovering an unknown ingredient in a classic cake recipe that makes it rise just a little bit differently. Another tantalizing idea is early dark energy. We think of dark energy as the dominant force today, but what if a small amount of this repulsive force also existed in the universe's infancy? This early dark energy would have acted as a temporary cosmic booster rocket, giving the expansion a brief, extra push just before the cosmic microwave background was released. This would have left a distinct fingerprint on the baby picture of the universe, a fingerprint that, if accounted for, could reconcile the two conflicting values for the Hubble constant. Then there is the most radical proposal of all, that we need to modify Einstein's theory of gravity itself. General relativity has passed every test thrown at it for over a century, but those tests have all been within our solar system or in strong gravitational fields like those around black holes. We have never directly tested its behavior across the vast, expanding emptiness of the entire cosmos. Perhaps gravity behaves differently on the largest imaginable scales. Perhaps it weakens over cosmic distances in a way we have not yet accounted for. This would mean the force that holds galaxies together and drives the cosmic expansion is not quite what we thought, forcing a rewrite of the most fundamental laws of physics. Each of these possibilities is a doorway into a stranger universe, a hint that our standard model, for all its success, is merely a close approximation of a much deeper and more bizarre reality. Dark matter provides the cosmic counterweight to this mysterious acceleration. While dark energy pushes, dark matter pulls. It acts as the universe's gravitational anchor, a vast, invisible scaffold woven through and around every galaxy and cluster. Think of it as the cosmic glue that holds the largest structures together through the sheer force of its gravity. We cannot see dark matter directly because it does not emit, absorb, or reflect any light. Yet we know it is there because of its profound gravitational influence. We see stars on the outer rims of galaxies whirling around at speeds that should fling them into the void, but something invisible with immense mass holds them in orbit. This unseen matter makes up about 27% of the cosmos, a dominant force of attraction in a universe being torn apart by repulsion. For billions of years, dark matter was winning the cosmic tug of war. Its collective gravity was putting the brakes on the expansion, slowing the rate at which space was stretching. Imagine rolling a heavy ball up a steep hill. Gravity pulls it back, steadily slowing its ascent. For most of cosmic history, the expansion of the universe was like that ball, climbing against the relentless pull of dark matter's gravity. Then, about 5 billion years ago, something shifted. The universe had expanded so much that space itself had become vastly more empty. Dark energy, which is a property of that empty space, grew stronger as the cosmos grew larger. Its repulsive push finally overcame the collective pull of all the dark matter. The cosmic ball reached the crest of the hill and began accelerating downward, except in this case, downward means flying apart faster and faster forever. This delicate balance, this billion-year struggle between two invisible giants, has written the entire story of our universe's expansion. It dictated the slow, steady growth that allowed galaxies to form and stars to ignite, and it now commands the headlong rush into a future of increasing isolation. This relentless acceleration points toward a deeply lonely future, a cosmic destiny known as the Big Freeze. As dark energy continues to stretch the fabric of space, it does more than just push galaxies apart. It fundamentally reshapes our cosmic neighborhood. Right now, we can still see light from galaxies billions of light years away, their light fighting against the expansion to reach us. But as the acceleration continues, a critical threshold will be crossed. Distant galaxies will be pushed away so fast that their light can no longer make the journey across the ever-widening gulf. They will first fade to red, then simply wink out of existence from our perspective, vanishing one by one beyond an invisible horizon. Our observable universe, the part we can ever hope to see, will shrink, not grow. The grand tapestry of the cosmos will recede into darkness, leaving our Milky Way and its closest galactic neighbors utterly alone in a vast black emptiness. Within this isolated island of stars, the final act will play out. All the fuel for new stars will eventually be consumed. The last stars will flare into existence, burn for billions of years, and then sputter out. White dwarfs and neutron stars will cool until they are black, cold cinders. Even the supermassive black holes at the centers of galaxies will, over almost unimaginable eons, slowly evaporate through a quantum process known as Hawking radiation. The universe will not end in a violent crunch or a fiery explosion. It will end in a whisper, the final state will be a near-perfect vacuum, a realm of profound cold where the temperature approaches absolute zero. Occasional, widely separated particles will drift through an infinite static darkness, unable to ever interact again. This is the heat death, a state of maximum entropy where all energy is evenly distributed, all temperature differences have evened out, and no work can ever be done again. It is the ultimate and irreversible end of cosmic activity, a silence that lasts forever. But the Big Freeze is not the only possible future. A far more violent and dramatic fate could await the cosmos, a scenario cosmologists call the Big Rip. This terrifying possibility hinges on one critical unknown, the nature of dark energy itself. In our current best model, dark energy is constant, a steady force represented by Einstein's cosmological constant. But what if it is not constant? What if the strength of dark energy grows over time? If dark energy's repulsive power were to increase, its influence would become overwhelming. For billions of years, its push has only been strong enough to overcome gravity on the vast intergalactic scale. But if it strengthens, its reach would begin to shrink. First, it would tear apart the cosmic structures held together by the weakest gravitational bonds. The great clusters of galaxies would be the first to fly apart, their members scattered into the void. As the force intensifies, it would target individual galaxies. The Milky Way, Andromeda, and all their neighbors would be shredded, their stars flung in all directions like dust in a hurricane. The terror would then move inward. Within a doomed solar system, the sun's gravitational grip on its planets would be broken. Earth would be ripped from its orbit, cast adrift into the ever-accelerating darkness. Next, the force would attack the planets and stars themselves. The gravity that holds a star together, the immense pressure that fuels its nuclear furnace, would be overcome. The star would be torn asunder in a final, silent flash. Finally, in the last moments, the fabric of spacetime itself would stretch so violently that it would overcome the forces that bind matter together. Molecules would be pulled apart, then atoms. The nuclei of atoms would be shredded, their protons and neutrons separated. Eventually, even the fundamental particles themselves might be torn from each other, unable to exist in a reality where space is stretching faster than the speed of light at every point. The universe would end not with a slow fade, but with a catastrophic, instantaneous rupture. Every single piece of matter would be eternally isolated, alone in a void where communication is impossible because space between them is expanding faster than any signal could ever travel. This ultimate disintegration could, in theory, happen at a precise, finite moment in the future, providing a definitive and apocalyptic end to time itself. This grand cosmic struggle between dark energy and dark matter plays out on a stage governed by a single, profound rule. The universe, for all its complexity, is fundamentally simple on the largest scales. Cosmologists call this the cosmological principle, and it is the bedrock upon which all of modern cosmology is built. It states two things. First, the universe is homogeneous. This means that if you take a big enough chunk of space, a cube a few 100 million light-years on a side, the average distribution of matter and energy will be the same everywhere. The galaxies, the dark matter, the dark energy, it is all stirred into a uniform cosmic soup when viewed from this grand perspective. Your particular spoonful might have a few more galaxy clusters, and mine might have a few less, but overall, the recipe is identical. Second, the universe is isotropic. This means it looks the same in every direction you look. There is no special axis, no preferred center, no cosmic north. From our vantage point, and from any other point, the large-scale structure of the cosmos appears statistically identical in all directions. This is the ultimate expression of cosmic humility. We are not in a special place. This principle is not just a philosophical idea. It is the key that unlocked the mathematics of the expanding universe. Because the cosmos is homogeneous and isotropic, the expansion must be uniform. It is the only logical possibility. You cannot have a lopsided expansion in a universe that is the same everywhere. This is why every galaxy sees all the others receding, just like every raisin in the rising bread dough. The cosmological principle forces this beautiful, democratic view of the cosmos. It allows us to use Einstein's equations of general relativity to describe the entire universe with stunning simplicity. Without this foundational assumption, our models would be an impossibly complex mess, trying to account for a unique center and a chaotic, uneven expansion. The principle gives us a stable foundation, a simple starting point from which we can build our understanding of everything, from the Big Bang to the ultimate fate of all things. Yet, this very principle is now being tested. As our telescopes peer deeper into space, they are mapping the distribution of galaxies and quasars on scales never before seen. The question hangs in the void: is the cosmic soup truly perfectly mixed, or will we find, on the very largest scales, a lump we never expected? Beyond the flicker of dying stars, another cosmic ruler is etched into the very architecture of the universe. It is called Baryon acoustic oscillations, a complex name for a simple, beautiful concept: frozen sound waves from the dawn of time. To understand this, we have to go back to the universe's first few 100,000 years. It was not silent. It was a seething, hot plasma, a dense soup of particles and light. In this primordial fluid, gravity was trying to pull matter together into clumps, while the intense pressure of radiation was trying to push it apart. This created a tug-of-war, generating powerful sound waves that rippled outward through the cosmic medium. Think of dropping a stone into a pond. The stone is a region of slightly denser matter, and the ripples spreading out are those pressure waves. Then, at the moment of recombination, when the universe cooled enough for atoms to form and light to travel freely, something crucial happened. The plasma vanished, and the sound waves instantly froze in place, their progress halted. The ripples were fossilized. This left a lasting imprint, a subtle pattern where matter was slightly more concentrated at a very specific distance from any initial clump. That distance, the radius of that frozen ripple, became a fixed standard ruler woven into the fabric of the cosmos. Today, that ruler is visible in the grand distribution of galaxies. When astronomers create immense three-dimensional maps of millions of galaxies, they do not see a random scatter. They find that galaxies are slightly more likely to be separated by a specific scale, about 500 million light-years apart. This is the echo of those ancient sound waves. It is as if every cluster of galaxies in the universe is sitting on the crest of a fossilized ripple. By measuring this exact scale at different distances, and therefore different eras of cosmic history, scientists can measure how much the universe has stretched since that light was emitted. It provides a completely independent check on the expansion history, a direct probe of dark energy's influence across billions of years, confirming the accelerating universe with a resonance that has been fading since the very first moment. This very expansion rewinds the cosmic film to its first frame. By measuring how fast the universe is stretching today, we can calculate the moment it all began. Think of a car traveling away from you at a constant speed. If you know its current speed and how far it has gone, you can easily work out when it started its journey. The universe is similar. The Hubble constant gives us the current speed of expansion, and by tracing the paths of galaxies backward, we find the moment when all of space was compressed into an infinitely hot and dense point. The mathematics is surprisingly elegant. The age of the universe is roughly the inverse of the Hubble constant. A faster expansion rate means a younger universe because it would take less time for galaxies to reach their current separations. A slower expansion implies an older, more leisurely cosmic growth. Our best measurements of the Hubble constant point to an age of approximately 13.8 billion years. This number is not just a guess, it is a cornerstone of modern cosmology, verified by completely independent lines of evidence. The oldest stars we can observe, studied through the science of stellar evolution, show ages just under this cosmic timescale. No star can be older than the universe itself. We also see confirmation in the very elements that make up our world. Radioactive dating of the oldest rocks on Earth and of meteorites that formed in the early solar system provides a lower limit for the age of the galaxy. The decay of elements like uranium into lead acts as a radioactive clock, ticking for billions of years and consistently pointing back to a cosmos that began its story 13.8 billion years ago. This remarkable convergence from the large-scale flight of galaxies to the nuclear furnaces in stars and the decay of atoms all tells the same story of our universe's profound and finite past. The color red holds a secret message from the distant cosmos. When astronomers analyze the light from a far-off galaxy, they are not just seeing its stars. They are reading a cosmic barcode written in its spectrum, the unique fingerprint of its chemical elements. But this fingerprint has been shifted. The familiar patterns are all there, but they have been dragged toward the longer, redder wavelengths of light. This is redshift, and its meaning is profound. For a long time, this shift was explained by the Doppler effect, the same phenomenon that makes a siren's pitch drop as the police car speeds away from you. But for galaxies racing away from us in an expanding universe, this analogy is only part of the story. The true cause of cosmological redshift is far stranger. It is not that the galaxy is simply moving through a static space like a car on a highway. The space between that galaxy and us is physically stretching. As a photon of light travels for billions of years across this vast gulf, the very fabric it is riding on is being stretched like a rubber sheet. This stretching pulls the light wave itself, lengthening its wavelength and shifting it toward the red. The longer the journey, the more stretching the light endures and the greater the redshift we measure. This is why redshift, denoted by the letter Z, is so much more than a speedometer. It is a direct measure of cosmic history. When we measure the redshift of a galaxy, we are directly reading how much the universe has expanded since the moment that light began its journey to our telescopes. A redshift of 1, for example, means the universe has doubled in size during the light's travel time. The light from that galaxy left when all the distances in the cosmos were half of what they are today. Every photon is a time traveler, and its redshift is the stamp on its passport, telling us exactly how much the cosmos has grown while it was in transit. This single measurement allows us to peer back through time, turning the sky into a layered history book where the most redshifted objects are the most ancient, their light telling stories from a younger, smaller universe. This cosmic redshift is not a perfect, uniform signal. The smooth expansion of space, the grand Hubble flow, is like a mighty river carrying all galaxies along with its current. But within this river, individual galaxies are like boats with their own motors, darting and swerving due to local gravitational tides. These random, individual motions are what astronomers call peculiar velocities. They are the gravitational fingerprints of the universe's lumpy structure. Our own Milky Way is not simply drifting with the cosmic current. We are being tugged sideways at a staggering 2 million kilometers per hour, pulled by the immense gravity of nearby cosmic structures. The largest of these is a mysterious, colossal concentration of mass known as the Great Attractor, a gravitational focal point hidden behind the dust of our own galaxy's central plane. This is not a single object, but a vast supercluster of galaxies whose combined gravity is drawing us and thousands of other galaxies toward it. To measure the true, pure expansion rate of the universe, scientists must perform a delicate cosmic subtraction. They first measure a galaxy's apparent velocity from its redshift. Then they calculate and subtract the galaxy's peculiar velocity, the component of its motion caused by these local gravitational pulls. What remains is the velocity due solely to the Hubble flow, the clean signal of the universe's expansion. It is like trying to measure the speed of a river's current by watching a boat. You must first account for the boat's own engine, its zigzags and turns, to understand the true, underlying power of the water carrying it forward. This meticulous process is crucial because failing to account for these local swerves would smear our measurement of the Hubble constant, adding noise to the very signal we are trying to isolate with such precision. Einstein's theory of general relativity gave us another tool to measure the cosmos, one that warps the fabric of reality itself. Massive objects like galaxy clusters bend the space around them, creating a natural curvature that acts like a giant lens. When light from a far more distant galaxy travels toward us and passes through this warped space, its path is not straight. It bends just as a beam of light would bend when passing through a giant piece of glass. This phenomenon is called gravitational lensing. In its most dramatic form, known as strong lensing, the effect is breathtaking. We do not see one image of the distant galaxy. We see multiple, smeared and stretched into brilliant arcs and rings of light encircling the foreground cluster. It is nature's own telescope, magnifying objects so faint and distant they would otherwise be forever invisible to our instruments. But these cosmic mirages are more than just beautiful curiosities. They are precise scientific instruments, because the geometry of the light bending depends on the mass of the foreground cluster and the relative distances between us, the lens, and the background galaxy. Astronomers can use it to measure cosmic distances directly. By carefully modeling how the light is distorted, they can calculate how far away the background galaxy truly is, independent of Cepheid stars or supernova. This provides a powerful third pathway to measure the Hubble constant. It is a completely different route up the cosmic mountain, one that relies on the warping of space-time rather than the brightness of stars. The results from these gravitational lenses are now adding a crucial new voice to the Hubble tension debate. Intriguingly, some early results seem to lean toward the faster expansion rate measured in our local universe, adding more weight to the argument that the discrepancy is real. Every time a new lens is discovered, it is another chance to peer across the universe using the fabric of space itself as our guide, offering a unique check on whether our cosmic rulers are true or if the universe is subtly tricking us all. That frozen ripple from the dawn of time has a precise and crucial size, a distance known as the sound horizon. This was the absolute limit, the farthest a sound wave could possibly travel through the seething primordial plasma before the universe cooled and became transparent to light. Think of it as the final, outer edge of every ripple in that cosmic pond, the ultimate echo from the Big Bang. This specific scale, this fossilized wavelength, was permanently imprinted onto the cosmos. We see its signature most clearly in the cosmic microwave background, in the preferred size of those hot and cold spots, but its imprint is also stamped onto the universe we see today. Because those ripples were waves of density, matter tended to clump most strongly at that specific distance from any initial seed. This is why, in our vast maps of the modern cosmos, we see that galaxies are statistically more likely to be separated by about 500 million light-years. It is the ghostly echo of that ancient sound, a cosmic drum that beat only for a few 100,000 years, yet defined the large-scale structure of everything for billions of years to come. This sound horizon is arguably the most important standard ruler we have for cosmology. Its true physical size can be calculated from first principles using the known physics of the early universe's plasma. We know exactly how long that sound had to travel, and we know the conditions of the hot, dense medium it was moving through. This gives us a ruler of known length frozen into the fabric of space at the moment of recombination. When we look at the cosmic microwave background, we are measuring the apparent angular size of this ruler on the sky. When we look at galaxy surveys, we are measuring its apparent length stretched across the cosmos. By comparing this known absolute size to how big it appears to be from our vantage point, we can perform a direct geometric measurement of the universe's expansion history. This is the heart of the Hubble tension. The Planck satellite's measurement of the sound horizon in the ancient CMB predicts one expansion rate. our local measurements of the same sound horizon, as seen in galaxy distributions, seem to require a different, faster rate. The ruler itself has not changed. Its true length is fixed by the laws of physics. The only thing that could be different is the cosmic journey that light has taken to bring us its image. This fundamental disagreement over the scale of our most trusted cosmic ruler suggests that the story of the universe's expansion is more complex than our standard model can describe, leaving us to wonder if the early universe was subtly different than we have always believed. Pinpointing the Hubble constant from our cosmic backyard is a monumental task of precision engineering. This local measurement relies on a chain of observations so delicate that a single misstep can throw the entire result into question. At the heart of this effort is the SH0ES project, a collaboration of astronomers dedicating years to shrinking the error bars on the universe's expansion rate. Their work begins not in the deep fields of space, but with a close neighbor, the Large Magellanic Cloud. This small satellite galaxy of our Milky Way is the anchor point for the entire cosmic distance ladder. To know the true, incredible brightness of a Cepheid variable star, you must first know its exact distance with absolute certainty. The Large Magellanic Cloud provides that critical first step. But how do you measure the distance to another galaxy directly? The SH0ES team used a method akin to celestial geometry, tracking the faint shadows of binary star systems as they eclipsed one another. By combining this data with other precise techniques, they established the distance to the Large Magellanic Cloud with an uncertainty of just 1%. It was a landmark achievement, fixing the foundation of the distance ladder more firmly than ever before. With this anchor set, the painstaking work could climb to the next rung. Astronomers identified Cepheid variables within the Large Magellanic Cloud, carefully measuring their pulsation periods and their apparent brightness from Earth. Because the distance was now known so precisely, the true, intrinsic brightness of these Cepheids could be locked in, calibrating Henrietta Leavitt's period luminosity relationship for the entire universe. Every Cepheid found in a more distant galaxy now had a certified wattage, but the path is fraught with obstacles. Interstellar dust is the eternal enemy of this work. These tiny particles scattered throughout galaxies scatter and absorb starlight, making distant Cepheids appear dimmer and therefore farther away than they truly are. If you do not correct for this cosmic dimming, you will overestimate distances and miscalculate the expansion rate. The SH0ES team must meticulously observe these stars in multiple wavelengths, from infrared to visible light, to measure the reddening effect of the dust and subtract its deceptive veil. It is a constant, meticulous battle against a faint, pervasive fog. Only after this rigorous calibration and dust correction can they find their ultimate targets, the Type Ia supernova, in the same galaxies as their Cepheids. This direct link from a calibrated Cepheid to a supernova is the gold standard. It transfers the known distance from the pulsating star to the cosmic flashbulb, telling us the supernova's true, phenomenal brightness. When they then find the same type of supernova in a galaxy so far away that its Cepheids are invisible, they know exactly how bright it should be. The faintness of its glimmer compared to that known brilliance reveals its true distance across billions of light years. This entire intricate process, from a nearby eclipsing binary to a dying star at the edge of visibility, represents thousands of hours of telescope time and a relentless pursuit of perfection. The result is a local measurement of the Hubble constant that is incredibly precise and stubbornly at odds with the early universe's prediction. This is not a guess. It is the product of a Herculean effort to measure our cosmic neighborhood, inch by precious inch, and its persistent disagreement with the cosmos's baby picture suggests that the foundation of our universe might be shifting beneath our feet. Hanging in the void 1,000,000 miles from Earth, a new eye has opened upon the cosmos. The James Webb Space Telescope was not built to solve the Hubble tension, but its unparalleled vision may be the very thing that breaks the deadlock. Its primary power lies in seeing the universe in infrared light. Think of interstellar dust not as a solid wall, but as a dense fog. Visible light, the kind our eyes see, gets scattered and blocked by this fog, making distant stars appear faint and misleading us about their true distance. But infrared light has a longer wavelength. It slips through the dust like a warm breeze through a screen door, largely unaffected. For astronomers, this is a revolutionary clarity. The James Webb Telescope can now observe the crucial Cepheid variable stars in galaxies that were once too dusty or too distant for the Hubble telescope to measure accurately. It sees these cosmic lighthouses not as blurry, reddened specks, but as sharp, distinct points of light. This allows for a far more precise measurement of their pulsation and, most importantly, their true brightness. By observing Cepheids in the same galaxies that host Type Ia supernova with this new, crystal-clear vision, the James Webb Telescope is rebuilding the cosmic distance ladder from the ground up, replacing its potentially warped lower rungs with ones forged in the fire of infrared precision. Is the discrepancy we see a simple error in our measurement of Cepheids, an error caused by dust and crowding that we could never quite overcome? Or is it a true crack in the foundation of physics? The James Webb Space Telescope is the ultimate arbiter, peering deep into the cosmic fog to finally tell us if our rulers are broken, or if the universe itself is far stranger than we ever dreamed. This accelerating universe we see today is actually the second chapter in a story of cosmic speed. The first chapter was far more extreme, a period of unimaginable violence called cosmic inflation. In the very first fraction of a second after the Big Bang, the universe did not just expand, it exploded in size, doubling its dimensions again and again in an eye blink of time. During this inflationary epoch, a speck of space smaller than a single atom was stretched to a size larger than our entire observable universe in less than a trillionth of a second. This was not driven by dark energy, but by a different, even more powerful repulsive force inherent to the fabric of the newborn cosmos. This incredible burst of growth solved profound mysteries that had plagued cosmologists for decades. It explained why the universe is so flat and uniform on large scales. No matter how curved or lumpy a tiny patch of space might have been, inflating it to cosmic proportions would have smoothed it out, like stretching a crinkled rubber sheet until its surface becomes perfectly flat. It also explained why the cosmic microwave background looks so similar in opposite directions of the sky. Those distant regions were once close enough to communicate and equalize their temperature before inflation blew them apart, locking their similarity in place. This inflationary spurt did more than just smooth the cosmos. It also planted the seeds for all future structure. The quantum fluctuations that shimmered in that microscopic patch of space were stretched to cosmic proportions, creating the tiny variations in density that would later, under the pull of gravity, grow into galaxies, stars, and planets. Then, as suddenly as it began, inflation ended. The repulsive field decayed, dumping its energy into the creation of the hot plasma of particles and radiation that we call the Big Bang fireball. The universe settled into the long, slower expansion powered by its own initial momentum and braked by gravity. For billions of years, this was the story, a gradual coasting. Now, dark energy has taken the wheel, initiating a new, slower but relentless acceleration. The cosmos is bookended by two accelerations, one at its birth of almost incomprehensible speed, and one in its old age, a quiet, persistent push into an ever deeper future. This staggering dominance of dark energy leads us directly to one of the most embarrassing problems in all of theoretical physics. Scientists call it the vacuum catastrophe, and the number at its heart is so immense it defies human comprehension. When we apply our most successful theory of the small quantum field theory to the idea of empty space, it tells us that the vacuum should be seething with energy. At the tiniest scales, particles and antiparticles are constantly flickering in and out of existence, a quantum foam of fleeting activity. This should give the vacuum an incredible energy density, a powerful repulsive force. The problem is the number. When physicists calculate this energy, the predicted value for the strength of dark energy is too large. It is not off by a little. It is off by a factor of 10 to the power of 120. That is a 1 followed by 120 zeros. This is the largest discrepancy between theory and observation in the entire history of science. To grasp the scale of this error, imagine predicting that a single feather would weigh more than the entire observable universe. Our best theory of the small and our best theory of the large are in violent, irreconcilable conflict over the nature of nothingness itself. The vacuum catastrophe is not a small puzzle. It is a screaming declaration that we are missing something absolutely fundamental about the fabric of reality. Either our understanding of the quantum vacuum is deeply flawed, or our conception of dark energy is completely wrong. This is not just a gap in our knowledge. It is a chasm so wide that it calls into question the very tools we use to describe the cosmos. This staggering mismatch is formally known as the cosmological constant problem. Our two most successful pillars of physics, quantum mechanics for the tiny world of particles and general relativity for the vast cosmos, give us two completely different answers for what empty space should be. Quantum theory tells us that the vacuum is not empty at all. It is a seething, bubbling sea of virtual particles, pairs of matter and antimatter constantly flashing into existence and then annihilating each other almost instantly. This quantum jitter should fill every cubic centimeter of space with an immense repulsive energy. When physicists calculate the strength of this vacuum energy, the number is astronomically large. Yet when astronomers look at the actual universe, they measure the effect of dark energy, and its strength is incredibly, delicately small. It is not zero, but it is 120 orders of magnitude weaker than the quantum prediction. To understand how preposterous this error is, imagine predicting that a single breath of air should have the explosive force of 1 trillion hydrogen bombs. The gap between prediction and reality is that vast, that incomprehensible. This is the fine-tuning problem that haunts theoretical physics. Why is the cosmos so perfectly balanced on a razor's edge? If the vacuum energy were just slightly stronger, the repulsive force would have been so powerful in the first moments of the universe that it would have ripped apart every proton and neutron before they could even form. Galaxies, stars, and planets would have been impossible. If it were slightly weaker or negative, the universe would have collapsed back in on itself in a big crunch long before life could ever emerge. The observed value of dark energy is just enough to drive the acceleration we see today, but not so much that it prevented our existence in the first place. This bizarre, precise calibration seems too perfect to be a random accident, leaving scientists to wonder if some deep, unknown principle of nature forces this cancellation, or if our very understanding of nothingness is fundamentally, profoundly broken. While our current telescopes have brought us to the brink of a crisis, the next generation of observatories is being built to flood us with answers. The Vera C. Rubin Observatory, poised atop a Chilean mountain, will not merely look at the sky, it will devour it. Every few nights, its immense mirror and giant camera will capture a complete panoramic image of the southern sky, a process it will repeat for an entire decade. This relentless survey will catalog tens of billions of galaxies, mapping the cosmic web in 3 dimensions with a detail we can barely conceive. It will also discover thousands upon thousands of distant supernovae, catching these cosmic flashbulbs as they ignite across the universe. This avalanche of data is not just about more numbers. It is about tracing the subtle contours of dark energy's influence with statistical power so immense that it could finally break the Hubble tension. We will see the universe's expansion history painted not with a few careful brushstrokes, but with a fire hose of information, revealing every bump and wiggle in its accelerating journey. Joining this ground-based behemoth will be the Nancy Grace Roman Space Telescope, a Hubble-like observatory with a field of view 100 times larger. While Hubble studied one galaxy at a time, Roman will survey vast swaths of the cosmos, performing its own wide-angle census of stars and galaxies. Its primary mission includes hunting for Type Ia supernova and measuring the shapes of millions of galaxies to study weak gravitational lensing, another powerful probe of dark matter and dark energy. Together, Rubin and Roman will act as a cosmic stereo system, one observing from the ground and the other from space, cross-checking each other's findings and eliminating hidden errors. They will measure the Barrian acoustic oscillations, those frozen sound waves, with such precision that we will know if the cosmic ruler has truly remained constant. This is not merely an upgrade, it is a revolution in scale. We are moving from studying individual landmarks to mapping the entire continent of the cosmos, hoping that within this deluge of light, the secret reason for the universe's conflicting speeds will finally be revealed. This fine-tuning of dark energy is so precise it seems to defy chance, pushing some of the brightest minds in physics toward a truly radical idea. Perhaps our universe is not the only one. The multiverse hypothesis proposes that what we call the cosmos is just one bubble in an infinite, frothing sea of universes, each with its own unique set of physical laws and constants. In this vast cosmic landscape, the strength of dark energy could be a random roll of the dice. In most of these other universes, the value might be too high, causing space to expand so violently that matter is torn apart before stars can ever form. In others, it might be too low or negative, leading to a swift and catastrophic collapse back into a singularity. We find ourselves in a universe where the number is, almost miraculously, just right. It is a value that permits the slow, graceful dance of galaxy formation and allows for the billions of years of stable stellar evolution necessary for planets and ultimately life to arise. This is known as the anthropic explanation. It does not explain why the dark energy density has its specific value through a fundamental law of physics. Instead, it suggests we should not be surprised to observe this particular value, because it is the only kind of value that allows for observers like us to exist in the first place. We are not at the center of the cosmos, but we may be living in a very special cosmic neighborhood, a rare and sheltered pocket of reality where the conditions are miraculously hospitable. While this idea offers a compelling way to sidestep the problem of fine-tuning, it remains deeply controversial. A multiverse is, by its very nature, almost impossible to test or falsify with our current scientific tools. For some, it is a logical extension of theories like cosmic inflation. For others, it feels like a philosophical surrender, an admission that we may never find a deeper, more elegant reason for the universe we call home. Our entire reality is built upon a cosmic illusion. Every star in the night sky, every planet, every single atom that makes up our bodies and our world is a rare and exotic ingredient in a universe dominated by things we cannot see. The stunning truth is that all ordinary matter, everything we know and love, accounts for a mere 5% of the cosmos. The remaining 95% is a complete and utter mystery. 27% is dark matter, the invisible gravitational glue holding galaxies together, and a staggering 68% is dark energy, the repulsive force accelerating the expansion of space itself. This means the fate of our universe, the very rate at which it is stretching apart, is governed by entities we can never touch, never bottle, and never directly observe. We are like sailors on a vast, dark ocean, sensing the immense currents and tides only by the way they push our tiny ship. We see the galaxies receding, we feel the gravitational tugs, we measure the accelerating expansion, but the ocean itself remains hidden. This is why cosmology is the ultimate detective story. Scientists are not just looking at the stars, they are piecing together clues from the shadows, from the subtle warping of light, from the faint echo of the Big Bang, and from the inexplicable motions of galaxies. They are trying to understand the nature of the vast, invisible ocean in which our 5% visible universe is merely floating. Every measurement of the Hubble constant, every investigation into the Hubble tension, is an attempt to understand the properties of these dark masters that rule our cosmos. We are left with a profound and humbling thought. We have mapped the heavens, we have unraveled the DNA of life, we have probed the inner workings of the atom. Yet, when we look out at the grandest scale of all, we find that we are essentially blind to 95% of existence. The universe is not what it seems. It is a ghostly realm, its true substance and its ultimate destiny written in invisible ink. The final fact may be the most profound of all, for the accelerating expansion does not just change the cosmos, it erases it. As distant galaxies vanish beyond an unreachable horizon, they take with them the very evidence of a shared cosmic history, leaving any future civilization stranded in an island of solitude. Imagine a library where the books on the farthest shelves are not just receding, but their pages are fading, their words dissolving into unintelligible whispers before the shelves themselves disappear into darkness. This is the future that awaits the universe. For any form of intelligence that arises billions of years from now, the cosmos will appear profoundly empty. The night sky, which for us is a tapestry of billions of galaxies, will for them be a near-perfect black. All that will remain will be the gravitationally bound local group, a handful of galaxies like our Milky Way and Andromeda, huddled together in a vast, eternal sea of nothing. The grand story of the Big Bang, the expanding universe, the cosmic web, all of it will be lost to direct observation. The clues we now take for granted will be gone, and with them, the context for understanding the universe's origin and fate. This places a fundamental limit on the longevity of knowledge itself. What happens when a civilization reaches a point where the cosmos offers no new data, no new frontiers to observe? The acceleration of space may ultimately enforce a kind of cosmic senescence, a final state where the resources for thought and energy are still present for a time, but the resources for discovery, for context, for a grand cosmic purpose have been permanently extinguished. In such a future, intelligence might persist for eons within its isolated galactic cluster, but its scope would be forever limited, its ultimate potential curtailed by the relentless, silent stretching of the dark. This journey through 30 cosmic facts began with a single, revolutionary observation. Edwin Hubble saw the galaxies fleeing, revealing an expanding universe where every point feels like the center. We then traced the cosmic distance ladder from pulsating stars to exploding supernova, only to find the expansion was not slowing but accelerating, driven by a mysterious force we call dark energy. We confronted the Hubble tension, a stubborn rift between the baby picture of the universe and our local measurements, a crisis that suggests our most fundamental models may be incomplete. We have explored the terrifying possibilities of a big rip and the profound loneliness of a big freeze, all while realizing that 95% of the cosmos is made of dark, unknown substances. The accelerating expansion of the universe stands as one of the greatest unsolved puzzles in all of science, a mystery written into the fabric of space itself. So what do you believe is the true nature of dark energy? Is it a constant force, a field that evolves, or something beyond our current imagination? Share your most fascinating cosmic thoughts in the comments below. If unraveling the universe's deepest secrets captivates you, subscribe for more journeys to the edge of our understanding.